Throughout the years, aircraft engineers have worked to design airplanes which exhibit favorable stability characteristics. Stability can be defined as a design characteristic that causes an airplane to return to steady flight after being disturbed. In any discussion of stability, two kinds must be considered: static and dynamic. Static stability is the initial tendency displayed by an object after it is disturbed from equilibrium. Let's use a marble to demonstrate static stability. When the marble is resting at the bottom, it is in equilibrium. If it is disturbed, its initial tendency is to return to its original position. This tendency is referred to as positive static stability. How an object responds over time, as opposed to its initial reaction, is called dynamic stability. An airplane with both positive static and positive dynamic stability does not immediately return to its original attitude after displacement. Generally, it goes through a series of progressively smaller oscillations. Since an inherently stable platform is highly desirable, a training aircraft is normally designed to exhibit both positive static and dynamic stability. To understand how this is accomplished, we must look at stability in relation to the center of gravity and three axes of flight. Since an aircraft operates in a three-dimensional environment, aircraft movement takes place around one or more of the three axes of rotation. They are called the longitudinal, lateral, and vertical axes of flight. The common reference point for the three axes is the airplane's center of gravity, or CG, which is the theoretical point where the entire weight of the airplane is considered to be concentrated. Since all three axes pass through this point, you can say that the airplane always moves about its CG, regardless of which axis is involved. The ailerons, elevators, and rudder create aerodynamic forces which cause the airplane to rotate about the three axes. When an airplane is banked, it rolls about the longitudinal axis. For a right bank, you rotate the control wheel to the right. This moves the left aileron down and the right aileron up. A closer look at the outboard section of the left wing reveals that as the left aileron moves down, the angle of attack and the camber increase. This produces more lift on the left wing. Conversely, as the right aileron moves up, the angle of attack and the camber decrease, which produces less lift. This difference in lift between the left and right wings causes the airplane to roll about the longitudinal axis. This roll will continue until you return the control wheel to the neutral position. At this time, the lift created by the wings will again be balanced. The airplane will remain in a banked attitude until you move the control wheel to the left. This reverses the process and creates a roll back toward wings level. Moving the control wheel fore and aft moves the elevator or stabilator and creates a pitching movement around the lateral axis. When the control wheel is moved forward, an upward force is created on the elevator, which pitches the nose down. Moving the control wheel aft will create a downward force on the elevator, which in turn will cause the nose of the aircraft to pitch up. The swinging movement of the nose to the left and right is called yaw and occurs about the vertical axis. This rotation is controlled by the rudder. When you step on the right rudder pedal, for instance, the rudder deflects to the right, which creates an aerodynamic force to the left. This causes the nose of the airplane to yaw to the right. Keep in mind that the rudder is not used to turn an airplane in flight. Its primary function is to align the fuselage with the direction of flight. Now let's look at stability about the lateral axis, which is called longitudinal stability. Longitudinal stability is normally obtained by locating the center of gravity ahead of the center of pressure, which is the point along the wing chord where lift is concentrated. This creates a slight nose-heavy condition. To balance this condition, a tail-down or nose-up force is created by installing the horizontal stabilizer with a slightly negative angle of attack. If your airplane pitches up because of a gust of wind or momentary control deflection, the horizontal tail surface moves toward a neutral or slightly positive angle of attack. This decreases the tail-down force, and because the nose-heavy condition is no longer balanced, the nose will return to the trimmed condition. Similarly, if the airplane pitches nose down, the negative angle of attack, and in turn, the tail-down force increases. This tends to return the airplane toward its trimmed attitude. Additional downward forces are imposed on the horizontal surfaces by the downwash created by the propeller and wings. This means that as you reduce power, the tail-down force decreases, allowing the nose to pitch down. Conversely, when you add power, the tail-down force increases and the nose tends to pitch up. Although a certain amount of pitch change with an increase or decrease in power is considered desirable, too much change would unnecessarily increase pilot workload. To help compensate for this, aircraft designers frequently raise the engine thrust line slightly above the center of gravity. This creates a nose-down pitching force when power is added and somewhat offsets the increase in tail-down force caused by additional downwash. Since pitch stability depends upon the difference in location between the center of gravity and the center of lift, the CG's location obviously plays an important role in how an airplane handles. By paying close attention to where and how much fuel, cargo, and people you load on an airplane, you can ensure that the center of gravity will remain within the limits set by the manufacturer. If too much weight is loaded in the front section of the airplane, the CG will be forward of the limit, making the airplane nose-heavy. If this happens, there may not be enough elevator or stabilator force available to rotate the airplane for takeoff, or to raise the nose of the airplane during the landing flare. A potentially worse situation occurs when an airplane is loaded with the CG aft of the approved range. In this case, the airplane will be very unstable in pitch. Even with full forward pressure on the control wheel, recovery from a stall might not be possible. Stability about the longitudinal axes is called lateral stability. Positive lateral stability is the tendency of an airplane to roll back toward a wings level attitude following displacement by a gust of wind or inadvertent control movement. The most common design feature used to attain positive lateral stability is wing dihedral, which is the upward angle of the wings with respect to the horizontal. When an airplane with wing dihedral is displaced in a roll, it will immediately begin to slip in the direction of the lower wing. This creates a higher angle of attack on the low wing, which in turn increases the lift on that wing, resulting in a tendency to roll the airplane back toward wings level. Stability about the yaw axis is referred to as directional stability. When an airplane yaws to the right or left, the large surface area that is behind the center of gravity acts like a big weather vane. This forces the nose of the airplane back toward the original position. So far, we have examined stability with respect to the axes of the airplane. Now let's take a look at some factors relating to the recovery from stalls and spins. It is important to remember that an airplane can stall at any attitude and any airspeed. However, there are other factors which can affect stall speed, such as weight and environmental conditions. As aircraft weight increases, more lift must be produced to support the increased weight. In order to maintain the same airspeed, a higher angle of attack is required to produce the lift necessary to support the increased weight, which in turn causes an increase in the aircraft's stall speed. How you distribute the weight also can have a significant impact on stall speed. For example, a forward CG shifts the balance of the airplane, causing a nose-heavy condition. To counteract this and balance the airplane, tail-down force must be increased. You can do this by increasing the angle of attack which causes an increase in tail downforce as well as a corresponding increase in lift and stall speed. Environmental factors such as snow, ice, or frost, which have accumulated on the surface of the wings, can also cause an increase in stall speed by altering the shape of the wing and disrupting the airflow over the wing. The additional weight and drag also causes an increase in the stall speed. Another environmental factor that can affect stall speed is turbulence. The rapid vertical gusts associated with turbulence can cause abrupt changes in the direction of the relative wind and can result in an increase in the angle of attack. Regardless of what causes a stall, you should be able to recognize the indications of an impending stall and take appropriate action to initiate a recovery before it occurs. Most modern airplanes are equipped with a stall warning device, which gives you a warning a few knots before a stall occurs. As the stall approaches, the flight controls will feel mushy. Just before the stall occurs, you will feel a buffeting or vibration. In addition, you may notice a pitching motion as well as a sensation of decreasing airspeed or a sinking feeling. To recover from a stall, lower the nose toward the horizon to decrease the angle of attack and regain lift. Simultaneously, smoothly apply maximum allowable power to minimize altitude loss and increase airspeed. As the airspeed recovers, you should maintain coordinated flight while adjusting power to a normal level. Keep in mind, the reason you practice stalls is not to become proficient at stalling the airplane. Rather, it is to learn to recognize the signs of an impending stall and recover before the airplane reaches a fully stalled condition. The characteristic corkscrew flight path results from an uncoordinated stall where the aircraft's wings are unequally stalled. The three phases of a spin are incipient, fully developed, and recovery. The incipient spin is the portion of the stall when rotation begins, to the moment when the spin has stabilized and the flight path is nearly vertical. At this point, the spin is fully developed. The final phase is spin recovery. To initiate the recovery, retard the throttle and neutralize the ailerons. Then reference your turn coordinator to determine the direction of rotation and apply full rudder opposite the direction of the turn. Now you should briskly move the yoke forward to approximately the neutral position. Depending on the airplane, you may need to move the yoke to a full forward position. As the rotation stops, neutralize the rudder and gradually apply back pressure to return to level flight. During the recovery, you should pay close attention to your aircraft's airspeed and load limits. It's important to understand that as an applicant for a private pilot certificate, you are not required to demonstrate flight proficiency in spin entries or spin recovery techniques. The emphasis in spin training is to provide you with an awareness of the conditions that could lead to an unintentional spin, as well as the general recovery procedures.